Hey everyone, welcome back to another video on P3 Maths. Today we're going to talk about vectors, topic revision, and we'll do some past paper questions as practice also. So the first thing that we need to revisit are the common notations that we are already familiar with from IGCSE also. So the easiest one are the column vectors. So column vectors, as the name suggests, they have components arranged in column format or column vector format. So x, y, z, they represent the displacement in x, y, and z axes. Another one is unit vector notation. How that works is we have the same vector, but it can be represented as in the form of I, J, and K. So I, J, and K are the unit vectors in X, Y, and Z axes. Similarly, we have point-to-point notation, which, as the name suggests, it shows where the displacement is originating, where it's starting, and where it's ending. So the same vector could be represented in column format or column vector format or unit vector format. So for example, you could have AB 2I plus 3J minus 5K. Or this could be represented as column vector also. So in column vector, it would be 2, 3, minus 5. Then the same thing can also be represented in general notation. You will often see letters written with bold A, B, or C, whatever they are. They will be just bold letters, but they represent same thing, just a vector. So for example, this A vector could be the same thing, 2I plus 3J. Now, these were the notations that some of them we were already familiar with. So let's move on. Next up is magnitude of a vector. So magnitude loosely means the length of a vector. So for example, how do we calculate this? We have a vector, let's say the same vector that we have, 2I plus 3J minus 5K. Again, this could be represented in column format also. Magnitude, on the other hand, magnitude of A is written as mod of A, modulus of A, or absolute value of A. If, for example, this was an AB vector like this would be written as AB mod. How do we find out the magnitude? You remember we sum the squares of the components, and at the end we take the whole square root. So 4 plus 9 plus 25. So 48 square root. So if you are familiar with, we don't actually have to use the calculator for this because this is easy. So this is 16 times by 3, so 4 times by 4 times by 3. So square root would be represented as 4 square root. Now, now that we know the magnitude of a vector, we can revisit what unit vectors were. So unit vectors basically like ijk. So these are the smallest vectors in the direction of a vector. So basically the smallest vectors in a given direction. Basically the direction would also be a vector. So smallest vector in a given direction and with a magnitude of 1. Magnitude of 1. So basically the magnitude of I, magnitude of j, magnitude of k are 1. But this applies to other vectors also. So for example, we had the same example over here, a, b, or a. We could find out the unit vectors in this direction also. So for example, we need to find unit vectors in the direction of this AB. So we have 2i plus 3j minus 5k. So what we will do to find out the unit vectors, there's a simple formula. So we divide AB, sorry, unit vector, we divide this with the magnitude of AB. So we have 2i plus 3j minus 5k, and we are dividing this by 4 root 3. We already found this over here. Now how this division works is all the components, all the coefficients will be divided. So 2 over 4 root 3i plus 3 over 4 root 3j minus 5 over 4 root 3k. Now this is not the simplified answer because we will need to rationalize these coefficients also, but otherwise this is how it's going to look. And if you take the magnitude of this unit vector, it would exactly be 1. Right. Now that we know the unit vectors, let's think or let's discuss the operations with vectors. So just like operations with scalars, we have sum, we have difference, addition, subtraction, we have product, we have division, quotient, whatever you want to call it. Same way, we have vector operations also, operations with vectors also. So these were with scalars, they exist for vectors also, but slightly differently. So first, let's take addition and subtraction. Of vectors. Now, since these vectors are not just numbers, they have directions also, so we can represent them visually also. Now, how this works. We are already familiar with the law of commutative commutation or commutative principle of addition, which states that a plus b is equal to b plus a. This holds for vectors also. So this holds for vectors also. How do we check this? So for example, let's say we have two vectors. Let's say we have one vector this, and let's say we have another vector this. And we want to check whether a plus b is equal to b plus a or not. So what are we going to do? We're going to start someplace because these are displacements. So basically we're going to start at some point. For example, let's say that we want to start over here. First is A, so 4 units to the right. This is our A. Then right at the head of A, we will start with B. So this would be, sorry, let's try again. Right, so this is your B. Now, if you notice what the final displacement is, or how the sum would actually look like, this would be the case, A plus B. And this would be the finish line or the end of this endpoint. What if we wanted to do B plus A? We would perform similar operation, but we will start with B. So we will start with B. So B would be looking, uh, why is it not making a straight line? Right. This is your B, and then A this way. And as you can see, B plus A is also offering the same, is also reaching the same endpoint. That means A plus B is equal to B plus A. So this commutative principle holds for addition also. And there's another name for this also, which is called parallelogram law of vector addition. Now, what about subtraction? What about subtraction? To get this, we recall what a negative of a vector means. So negative of a vector is is an identical vector but in opposite directions. So a parallel vector, identical in magnitude but in opposite direction. So we had A going like this. So minus A would go opposite way. It would be exactly identical to each other in magnitude. They would be parallel, but just simply opposite. So we had B, so minus B would be going opposite way. So by that, this would be minus B. So we could perform the same addition with negative of vectors also. So remember the principle we use in scalar addition, that A minus B could also be written as A plus minus B. So if we want to do A minus B, we could start, for example, over here, go in the direction of A. And sorry, we had minus B over here, so I need more space. Minus B would be this thing. So minus B goes this way. So this is your minus b. So the final displacement would be this a minus b. This is your resultant vector. This is how we deal with vector subtraction. Now, moving on. These were vector addition and subtraction. Now let's take to understand this, we need to know a few more things and we'll practice this concept also. So we are familiar with the concept of general vectors and position vectors. So we know general vectors, just like the vectors that we were talking about, they can be placed anywhere. In the entire 2D or 3D space. But position vectors originate from origin. That means the tail of that vector will be at 0, 0. Let's take an example of this. Let's say we have axes. We have a few coordinates. Let's say we have this. This is, let's say, A, and this is 2, 3. And let's take this one, which is 2, 4, 6, 7, and 2. First off, we now know the position vectors, how position vectors work. So position vectors will start from origin. So we can convert coordinates into position vectors. So position vectors will always start from origin. So what that means is converting this information into position vectors, we can represent this in column vectors 2, 3, or it can also be written as 2i plus 3j. Similarly, OB will be written as 7, 2, or 7i plus 2j. Either way is fine for us. But what if we want to find out a different vector? Let's say AB, AB, right? So what do? Now we need to start with A and end at B. There are two ways to do this. Okay, so there are two ways to do this. Either way, you have to imagine that you yourself are traveling from in this space. So if you notice, to go from O to B, so let's write over here. So to go from O to B, you can go from O to A and then A to B. You see, this is the start, this is the end, and this A is the intermediate point. This is one way of going there. Another way to find out AB, sorry, AB and AB could be written as OB minus OA. And minus OA is just the negative of the vector OA. Now, AB. For AB, another way to do this, you can imagine yourself displacing from A to O, and then O to B. This would give you also AB. And remember, AO is again minus of OA. So minus OA plus OB, exactly the same thing that we had over here. No difference. So no matter how you want to understand this concept, you can see that this you would arrive at the same answer. Now, if we use these values, how this would work? OB minus OA, OB is 7, 2. Again, you can do it the column vector form or the unit vector form. It all depends on how the question is actually given. If the question is given in the form of IJK format, then it's better to stick with IJK format. And oh, sorry, OA is 2, 3. So the vector would be 7 minus 2, 5, and 2 minus 3, minus 1. And if you notice, 5 units towards the right, 1 unit down, this is exactly what 5 minus 1 looks like. Right. Okay. Now, to practice this concept, these concepts up till now, what we have learned, let's take a past paper question example. Okay, so let's see this. The points A, B, and C have position vectors relative to origin O given by OA I plus 2j plus 3k, OB is this, OC is this. A fourth point D is such that the quadrilateral ABCD is a parallelogram. Find the position vector of D and verify that the parallelogram is a rhombus. Now let's draw a general diagram for this to understand how this might look. Although again, this will not be the exactly how it looks, but a little general picture of this is necessary. So for example, we have this. This is your origin O. This is your A. This is your B. This is your C. This is your D. Now we have OB and OA and OC. So sorry. Let's make it a little bit this way, a little bit further away. So this is O. Right. Okay. Now D is such that the quadrilateral ABCD is a parallelogram. We know the properties of parallelogram. We know that DC is parallel to AB and AD is parallel to BC, which means that in vector form they will be equal. So the vector AB is equal to DC, and also AD is equal to BC. So either way, we can actually find this. So let's say, for example, we expand this way in position vectors. So position vectors, so in terms of position vectors, AD can be written as OD minus OA, and BC can be written as OC minus OB. So this means that OD we can easily find out by just simply taking OA on the other side, because we know the rest of these. So OC, 2i plus 5j minus k, minus OB is 4j plus k, and OA is, what was it? 1, 2, and 3. So we don't need the brackets over here. 2, and 3. So to resolve this, We know negative of a vector. How does this work? So all the components will be, the signs of all the components will be reversed. So 2i plus 5j minus k minus 4j minus k plus I plus 2j plus 3k. Now all we need is component by component addition. So 2i plus I is 3i, 5j minus 4j is j plus 2j, 3j, and minus k minus 2k plus 3k is plus k. So this is our OD. So this is the first half of this question. Now we need to verify that the parallelogram is a rhombus. Now we have established that AB is equal to DC. This means that not only they are parallel, this also means that the magnitude-wise, magnitude of AB is equal to magnitude of DC. Same goes for AD and BC. So magnitude of AD is equal to magnitude of BC. However, for a rhombus, we just need one additional uh, condition, that these adjacent lengths, either AD, so for a rhombus, for this parallelogram to be a rhombus, for ABCD to be a rhombus, all sides have equal length. All sides have equal length. Now we know that these two sets individually they are equal, but we just need to connect them that indeed that this is the case. All of these lengths are equal. So what we can do, we just need to compare the adjacent lengths. So if the length or magnitude of AB is equal to AD, then it will be a rhombus. Then ABCD is a rhombus. This is the only condition we need to check, because the rest of the lengths we already know, or we already know that they are equal. So we know AB is equal to DC and AD is equal to BC, but we just need to confirm that whether this set of values matches this set of values or not. So let's figure this out. First off, we would need to find out AB and AD first. So AB is OB minus OA. So OB is 4j plus k minus OA is I plus 2j plus 3k. So this would be 4j plus k minus I minus 2j minus 3k. And this simplifies to minus I, 4 minus 2, 2, and minus 2k. So magnitude of AB would be 1 squared plus 2 squared plus 2 squared. So 1 plus 4 plus 4 is 9. So length or magnitude is 3 units. We need to do the same thing with AD. So OD minus OA. So OD we have found out to be 331. Let's do this with all the, okay. So one thing you need to remember, if the question is given in algebra format, working you can do in column format, but answer should be given in ij format. So we'll stick with ij format. So 3, 3, and 1. So 3i, 3j plus k minus, we already know what happens with the minus OA part. So all these components, the signs will be reversed. So we will end up with 2i plus j and minus 2k. So the length of AD is 2 squared, 1 squared plus 2 squared. Again, it's 4 plus 1 plus 4, square root of 9, that is 3 units. So, uh, sorry, length of AB is equal to length of AD. Therefore, ABCD is a rhombus. Sorry. All right. So this was an example that where we had to use position vectors, addition, subtraction, magnitudes, and just a basic understanding of what makes a parallelogram a rhombus. Now, we did addition and subtraction operations with vectors. Now let's talk about multiplication. So multiplication with vectors. Now there are different possibilities. One possibility is that you have a scalar multiplied with a vector. We will see that in a second. But for a vector multiplied with a vector, there are two possibilities. So when we use something called dot product, the product is a scalar. So this is known as a scalar product. In the syllabus, it is written as scalar product, but it can also be called dot product. Similarly, something which is not in the syllabus, but just to finish the discussion, another way to have a product of vectors is a cross product of vectors, and the product of such a multiplication, no, or such a product is a vector. That's why it's called a vector product or a cross product. This one is not in our syllabus, so we don't have to worry about this. But these ones are. Now, let's talk about the first one, scalar multiplication with a vector. So what this means is you have a vector, let's say a scalar multiple it could be lambda, it could be k, it could be m, it could be n. So when we multiply a scalar multiple with a vector, we get another vector. So this is vector b. This could also be written this way. So a is equal to lambda b. But obviously these two lambdas would be different. more often than not, you will actually see this. So this A is a vector, this is a scalar multiple, and this is a vector. So this means that when you multiply a scalar with a vector, you get another vector back. But there are two other properties associated with this. A and B are parallel vectors, which means scalar multiplication with a vector creates a vector parallel. Secondly, that their magnitudes are also related by the same scalar multiple. That the magnitude of A is lambda times by magnitude of B. So these are the two results that come from scalar multiplication with vectors. So let's see an example. So let's say you have vector, let's say B vector 3 minus 1, 3. And we multiply this by, let's say 2, 2b. A is 2b. So what that means is to find out A, we need to multiply 2 with the vector 3 minus 1, 3. So component by component multiplication, 2 times by 3, 6, minus 2 and 6. So this has created a parallel vector A. But how do we show that their magnitudes are also related by the same scalar multiple 2? Simply by just finding out their magnitudes. So magnitude of B is 3 squared plus 1 squared plus 3 squared, which is 9 plus 10 plus 9, right? 9 plus 9, 18, square root of 19. A, on the other hand, 6 squared plus 2 squared plus 6 squared. So 36 plus 4 plus 36. So that would be 36 plus 36 is 72 plus 4, 76. Now, we're familiar with the IGCSE rules. We can, figure out common factors. So 2, 38, and then 2, 19, and there you go. So 4 times by 19, so we will bring out 2 square root of 19. So as you can see, 2 was the factor. So the magnitude of A is 2 times by the magnitude of B. So this is a result that you should already know and not always have to calculate. Okay, moving on. This was the scalar multiplication with a vector. Now, vector multiplied with a vector with a scalar product. So now it's an interesting thing. Scalar product. This time we'll look at both column and the IJ format. So scalar product, again, as the name suggests, produces a product of two vectors where the product is a scalar, but we have to perform that in a very specific way. So let's say you have a vector 2 minus 3 and b vector is minus 5 and 5. We need to find out the scalar product between them. Column vector way is very easy, but to do it with the IJ format requires a little bit of understanding. So few things we need to know before we do this. So scalar product depends on angle between vectors. So if the vectors are parallel, scalar product would be 0. And if they are perpendicular, oh sorry, scalar product would be non-zero, sorry. If the vectors are perpendicular, scalar product would be 0. Which means that when we expand these to unit vectors, I dot I would be 1, but I dot j or I dot k would be 0 because I is in the same direction, but j and k are perpendicular to I vectors. Same case with j dot I is 0, but j dot j is 1, and j dot k, j dot k, 0. Same case with k dot I, 0, j dot k, 0, and k dot k, on the other hand, is 1. So there is a very specific result that comes out over here. We will actually see, so you will see this over here. It comes out to be equal to square of their, or product of their magnitudes. So what that means is I dot I is 1, so the unit vectors, their magnitude was already 1. Now, let's see this over here. Let's see these two vectors, which are obviously not parallel, but let's verify that anyway. So A dot B, how do we do this in this form, column vector form? We just simply multiply component by component and then just add the results component by component. So 2 times by minus 5 plus minus 3 times by 5. So minus 10 plus minus 15. So this gets us minus 25, right? What if this had been in the IJ format? I will just do it once to show you these values, these representations also, and then you don't need to do this. So for example, you have two vectors, C, let's say 2I minus 3j plus 3k, and B vector is, let's say 4I plus 3j plus k. So let's see this. So we can use the distributive principle over here. Distributive principle of multiplication. Actually, this would be a very long process, but so I'll stick to 2D. So C dot D, you can do this process 2I minus 3j dot 4I plus 3j with the distributive principle of multiplication. So 2I times by 4I plus 3j. Just hang on for a second and then you will see. And then minus 3j dot 4I plus 3j. So you will get 2 times by 4, 8 I dot I plus 2 times by 3, 6 I dot j minus 12 I dot j and minus 9 j dot j. Now notice that I dot I and j dot j were at values of 1, but I dot j or any other vector would have been 0. So these components would be 0. And I dot I and j dot j have values 1. So you will get 8 minus 9 equals to minus 1. So this was the principle behind the full uh, multiplication, but you don't have to repeat this process again. You can just do component by component multiplication and simply just addition. Now, what happens when they are parallel? So let's see this over here. We had two vectors, 3 minus 1, 3, and 6 minus 2, 6. Let's see another example. So A vector was 3 minus 1, 3, and B vector was 6 minus 2, 6. These two vectors are obviously parallel to each other, and as you can see that it's the same coefficient or same multiple that is applied on all the components, either direction. So 6 divided by 3, 2, minus 2 divided by minus 1 is 2, 6 divided by 3, 2 again. So now if we do A dot B, oh, sorry, I should have done this in IJ format. So 3 times by 6, then plus minus 1 times by minus 2 plus 3 times by 6. So 18 plus 2 plus 18. So 36, sorry, 18 plus 18, 36, and then 2, 38, which is, if you notice, the magnitude of A times by the magnitude of B. So magnitude of A was 2 root 19, and the magnitude of B, sorry, the other way around, sorry. The magnitude of A is square root of 19, and the magnitude of B is 2 root 19. So basically 2 times by 19, so 38. We could have done this in the IJ format also. But what does this show us? That the dot product is actually related to the magnitudes of the vectors. How? The derivation is not important, but A dot B is related to magnitude of A, magnitude of B, cos of theta. So when theta is 0, cos of 0 degrees is 1. And when theta is equal to 90 degrees, cos of 90 is 0. So this can be used to find out the angle between two vectors also. Now let's see some past paper question examples to practice this concept. Okay, now let's look at this. With respect to the origin O, the position vectors of points A, B, and C, D are given by these that are given. Show that AB is equal to 2 times by CD. So first thing we can do, we know that how to find out AB now using position vectors. So AB is going to be OB minus OA. So since they are already given in column vector format, we can do 4 minus 1, 1 minus 2, 1, 5. So component by component subtraction, 4 minus 2 is 2, minus 1 is minus 2, and 1 minus 5 minus 4. Similarly, we can do CD, that is going to be OD minus OC. So OD is 3, 2, 3 minus OC is 1, 1, 2. So 3 minus 1, 2, 2 minus 1, 1, and 3 minus 2, 1. Notice that in the question, they did not use the arrows over there. That means that they are not talking about vectors. They're talking about lengths, or in other words, modulus, magnitude. So what we can find out are modulus of AB, which is the length of AB. So 2 plus 2 plus 4 squared. This is method 1. Method 2 is slightly more apparent, but let's carry on. This is going to be 2 squared plus 1 squared plus 1 squared. So this one, 4 plus 4 plus 16, 4 plus 4 plus 16, that is 24, which can also be written as 2, 6. This one, on the other hand, 4 plus 1 plus 1, that is root 6. So as you can see, the magnitude of AB, therefore, is 2 times by the magnitude of CD, or the length way. Method 2 relies on the parallel lines thing with what we just did. So if we have AB, if we want to see whether these two are parallel or not, we write lambda in this. So 2, 1, 1. They were not parallel to each other. As you can see that the component by component are different. So only length way we can actually do that. If they were parallel, we could say that lambda was equal to 2. So the magnitude of AB would be equal to 2 times by the magnitude of CD. But only and only if these two vectors were parallel, but they were not parallel. So we only need to work with length, which is simply using this formula. Now, find the angle between the directions AB and CD. So we have found out already AB and CD. So, and we have also found out their magnitudes. So there's a very easy way how this is all going to be used. So B, we know that the AB dot product with CD is going to be equal to magnitude of AB times by magnitude of CD times by cos of theta, where theta is the angle. Now what we can do, we can find out the dot product between them. So we had 2 minus 2 minus 4 dot 2, 1, 1. Magnitude of AB was 2 root 6. CD was root 6. And this is cos of theta. So on the left side, it's component by component, multiplication, and then addition. So 2 times by 2, 4, minus 2 times by 1, minus 2, and then minus 4. On the right hand side, 2 times by 6 becomes 12 cos theta. So 4 minus 4 becomes cancelled, so minus 2 divided by 12. Cos theta would be minus 1 over 6. So let's do cos inverse of minus 1 divided by 6. We get 99 point, sorry, what was it? 594. So the question asked us for the acute angle. That means we need the acute angle. Oh, sorry, the question does not ask for the acute angle. Okay. So the angle between them is this. So that's it. That's the answer. Now let's see another similar question. Okay, so let's see this. With respect to the origin O, the points A and B have position vectors given by this and this. Show that OA and O is equal to OB. So again, they mean the length. Okay, so if the arrows are not given, they mean the length. And use a scalar product to calculate the angle AOB in degrees. All right. So first off, the length. So length OA. So that is just going to be 2 squared plus 1 squared whole under root. And OB length is 1 squared plus 2 squared. Notice that they both come out to be 5 squared. So therefore, length of OA is equal to length of OB, or magnitude of. Now use a scalar product to calculate the angle AOB in degrees. Okay. So first off, what we can do, we can find out the dot product, and we can use the dot product formula also. So OA multiplied by OB cos of theta. So OA dot OB, we have 2i minus j dot j minus 2k equals to square root 5 dot square root 5 dot square root theta. So we just need to multiply I component with I component, j component with j component, and k component with k component. So there's only like j component with j component. So minus j times by j is going to be minus 1 equals to 5 times by cos of theta, which makes cos of theta equals to minus 1 over 5. So we can find out theta by just doing cos inverse of minus 5. So cos inverse of minus 1 over 5 is 101,536 or 101.5 degrees. Okay, now midpoint of AB is M. Point P on the line through O and M is such that PA is equal to OA. So let's make a little bit of diagram for all of this. It helps with the visualization part. So for example, AB is this thing. This is your A, this is your B. Okay. We have a midpoint somewhere M. Okay. And point B on the line through O to M. There's a line through O to M and there's some point P over there such that PA ratio OA. So PA ratio OA is √7 ratio 1. Okay, all right. Find the possible position vectors of P. So first off, we need to locate where M is. So B part. So first off, we need to know where M is. They said it's the midpoint of AB. So we have this. Let's say this was the axis O. Let's say this is O. This is B. So if you consider, there's an easier formula for this also, but I want you to see how we have actually, sorry, OA and OB. And this is M over here. So to find out OM, what we can do is first we can find out AB. So AB we know is OB minus OA. We are already familiar with this. And OM, or sorry, AM is half of AB, which is means half of OB minus OA. So if we want to go from O to M, what we can do, we can go to OA and then A to M. So to go from O to M, you can go OA plus AM, which leads you OA plus half OB minus half OA, which gives you half of OA, because OA minus half OA is just half OA plus OB. Now this is the general form for the finding the midpoint. OM was the midpoint of AB, so this is the general form also, and we have actually seen how to derive this. And this is now the OM. We can find out, since we have the vectors, we can find out. So OA was this 2i minus j. So half of 2i minus j plus j minus 2k. So j and j get cancelled, and 2 and 2 divided by 2. So this is just I minus k. Okay, so that is OM. Now, P is along the line of M. P is along the line of M, which means it follows the parallel line relationship. And that O, P, and M are collinear points. So O, P, M are collinear, which if you remember from IGCSE, that means that OP is some multiple of OM, which means that they are parallel vectors. So we can assign some scalar multiple with OM I minus K. Okay, so some lambda I minus lambda K. Now, let's go back and see what the distance condition was. The PA and OA, the distance between PA and OA. Okay, so we need to find out the expression for the distance between PA. So PA is OA minus OP. OA is 2i minus j, and OP is lambda I minus lambda k, which simplifies to 2i minus lambda I minus j plus lambda k. So the I component is 2 minus lambda, j component is 1, and lambda component is just lambda. Sorry, this is I, this is k. Now, we know the magnitude of OA. That was root 5. We just need to figure out the expression for the magnitude of PA. So this would be 2 minus lambda whole squared plus 1 squared plus lambda squared. So first let's expand it this way, then we will compare that. So 2 minus lambda squared. So this is going to be 4 minus 4 lambda plus lambda squared plus 1 plus lambda squared. So as you can see, this will be becoming a quadratic equation. So this becomes lambda squared for lambda squared, 2 lambda squared, and minus 4 lambda, and plus 5. On the other hand, we had OA. We know OA whole squared was equal to 5 because the length of OA was root 5. So now all we need to do is to use the ratio. So ratio of PA squared over OA squared equals to root 7. So the condition that was given was PA ratio OA root 7 ratio 1. So basically we can square the both sides. So when you square the both sides, this becomes 7 over 1. So you have 2 lambda squared minus 4 lambda plus 5 over 5 equals to 7 over 1, and when you cross multiply, it becomes 2 lambda squared minus 4 lambda plus 5 equals to 35. Now, this requires a little bit of simplification. So 2 lambda squared minus 4 lambda plus 5 minus 30 is minus 30. Divide by 2 on both sides. This becomes lambda squared minus 2 lambda minus 15. So I think 3 and 5 could be the proper values. We can use the sum and product rule. So we have lambda squared, we have minus 15, we have minus 2 lambda. So this is lambda times by lambda. This is 3 times by 5. So 5 lambda minus 3 lambda. So the only way we get a negative if this 5 was negative. So we get lambda plus 3 times by lambda minus 5 equal to 0. So either lambda is -3 or lambda is 5. Both of these will give us different positions for OP. Both of these different will give us different positions for. So we had OP lambda I minus lambda k. So when lambda is equal to -3, you get OP minus 3i plus 3k. And when lambda is equal to 5, you get OP 5i minus 5k. And that's about it for this question. All right, let's call it a day over here. Hopefully in the next video, we will look at the equation of the vector lines, and then we will continue some past paper questions also. All right, hopefully see you in the next video. Bye-bye.